observation method, a new tool for the bridge scour engineer. This is a method that has been developed starting in about 2005, sponsored by the Texas Department of Transportation, where John Delfia was the contact. Project was about $400,000. Followed with another 3-year project with the Massachusetts DOT to expand it, where Rich Murphy and Hanan Fouad were the contacts, $300,000. And we worked through CDM Smith at Texas A&M University. We finished the methodology to expand it to all the continental United States. And I estimate that this was to the tune of another $300,000. So this is $1 million project that took place over the last 13 years. So scour depth, you know about all this, about mud scour, beer scour, contraction scour. And the problem posed by the Texas DOT was the comparison between measured and calculated scour depth by the current method, HEC 18, exhibits a lot of scatter. Secondly, the comparison between measured and calculated scour depth by current method, HEC 18, shows excessive conservatism on the average. And this is an example of, on the vertical axis, predicted scour depth versus measured scour depth. This is the Landers-Mueller USGS database. And you can see that on the average, the predicted scour depth is 3.2 times larger than the measured scour depth. But this is actually necessary. This overconservatism is necessary because you still have some of the points that are below the 1-to-1 line. And so while this doesn't look like a very good picture, I want to make an important statement here. I have a lot of respect for people like Everett Richardson and Stan Davis, who developed this methodology because at that time there was not much available, and what they developed really saved a lot of lives by keeping our bridges safe, safer since this methodology has been developed. This is another example for abutment scour, and again you see the conservatism on the average, but the large scatter. So there are two things associated with the current technique. We did our own evaluation by collecting 11 bridges case histories and applied the HEC 18 methodology. And in this case, so this is again predicted versus measured, 1.77 times larger, and the scatter again with an R-square of 0.3. Going down to the bottom of the issue, by comparison, here's the scatter we get from the observation method. We have a 1.06 regression line, and the R-square has increased dramatically to 0.86. So I want to talk to you of how we were able to improve the prediction process in that fashion. But before I do that, I wanted to share with you, at least in the first part, first a few pictures to put you in the right mood. Big holes, loss of support. Unfortunately, you probably have seen those types of things. But we're not the only country that has a problem with this. This is Portugal, loss of deck. This is Japan, loss of pier, 1, 2, 3. Note that the bridge deck is still standing, the pier is gone. And then loss of bridge. The railroad track is still there, but the bridge is gone. So over the course of, I've been working in Scour for 30 years. In the first 15 years, I did a lot of flume tests and tried to develop a lot of equations, particularly for the cohesive side of the soils. You see here a test in clay. Note that the hole is on the side of the pier. If you put your instrument to monitor the scour hole in front of the pier, you're going to conclude that you don't have a scour hole, when in fact there is a scour hole. It's just in a different location. So beware about this. We did some contraction scour. This is a 12-foot wide flume, contraction scour, and abutment scour test in cohesive soil. We developed this erosion function apparatus where we put the sample from this, and we push it out of the steel tube in the water flow, and the water erodes it, and we push the piston only as fast as the water is eroding the material on top of it. And you can see here the tube, and here's the water coming through, and this way we monitor we quantify the erodibility of the material. So if you look at this, here is scour rate as a function of velocity, and for sand you might be at 1 meter per second, 3 feet per second, and you have 1,000 millimeters per hour, so 1 meter per hour. But if you have a clay, for the same type of tests at 1 meter per second, you have only 1 millimeter per hour. So the huge difference between the sand and the clay in this particular case. This is why I think it's critical that in any equation, scour depth equation, we need a soil parameter. Because if we don't have a soil parameter, we cannot make the difference between 1 millimeter per hour and 1,000 millimeters per hour. And one of the limitations of the current HEC-18 sand methodology is that we don't have a soil parameter in the equation. So this was the $50,000 piece of equipment. We have the $50 piece of equipment. And for those of you, how many of you are geotechnical engineers? Wow, 3, 4. So for those of you who are geotechs, you know about the pocket penetrometer. Very useful tool, crude, but gives us some valuable information in the field in very little time. So the pocket erodimeter is kind of a parallel to the pocket penetrometer. We've developed, starting about 4 years ago, the borehole erosion test. As geotechnical engineer, we drill a lot of boreholes. And when we drill boreholes wet, we send the water or the mud down the center of the rods. It goes down to the bottom of the hole. It comes back on the side of the hole. And we've been drilling boreholes for hundreds of years. These are erosion tests. But we never measured the diameter of the borehole. So what we do is essentially we have a borehole caliper. Here it's retracted, here it's expanded. We go to the bottom of the borehole, we pull the caliper, and we can monitor the size of the hole as we pull up. And here are two profiles. This is the center of the borehole. We're down about 13 feet depth. And you can see that for various velocities, there's not much erosion from 0 to maybe 8 feet. And then here's a sand layer. We didn't know it was there. We just tested the borehole. And so you can identify easily. You have a profile, and here is probably an intermediate erosion type of material. Here in a different site, the sand at the top with a clay layer right in between, and you can see this profile of erodibility as a function of depth. So when you can do this, you don't need to do the FA. And I just put myself out of business. But I think it's quite useful to be able to see a complete profile of the soil with a very simple test. Everybody has drill rigs. You just need a borehole caliper, and then you get this kind of records. We're finishing a NCHRP project on the correlation of common soil properties with erodibility properties. So critical shear stress, critical velocity, slope of the erosion function, erosion categories. We've collected 1,000 erosion tests. We ran 400 ourselves, whole erosion test, jet erosion test, EFA, borehole erosion test, and we collected 600 additional tests, and they're all in a spreadsheet, and hopefully in a few months you can have access to that spreadsheet and play with it as you wish. It's an addressable spreadsheet, so you can go in there and say, well, my soil has a plasticity index of 40. Give me all the tests that you have with clays that have plasticity index of the order of 40. So you can look at this, and we have new correlation equations, including uncertainty associated, and we call it time-year erosion. And then we've updated these, so this is erosion rate versus velocity, and these are erosion categories here with the classifications. This is the old chart, the one that's in the current HEC 18 circular, and it's being updated because of the 1,000 test spreadsheet that we have accumulated. And this is the critical velocity as a function of grain size. And you can see again that on the coarse grain soil, we have a reasonable correlation. On the fine grain soil with D50. On the fine grain soil, as Joe Krolak told us yesterday, we cannot rely on D50 alone because it doesn't work. We've done some simulations. I'm going to pass on this. So observation method. After 15 years, from 1990 to 2005, working on flume tests and doing this, in the end, I looked at predicted versus measured, and we hadn't improved things very much. I was frustrated, and that's why I started to think completely differently, and this is how this observation method developed. It's 4 steps. 1, you observe the maximum scour depth at the site. 2, you find out the maximum flood the bridge has seen. 3, you extrapolate the field measurements to predict the future scour depth for a future flood that you're worried about, and then you compare that future scour depth to what's allowable for your particular foundation. And this came out in cooperation with the Texas DOT out of their frustration because the HEC 18 would give them 30 feet, let's say, and the inspector would come back from the field and would say, well, you know, we've seen only 2 feet of scour. And this bridge has seen some pretty big storms. But they didn't have anything to prove that. So that's how it started. So first, the bridge site, either you go through the guardrail and get a profile, or you use another technique to do sonar, for example, to record the bottom of the river. And you have these, what we call ZEMO, the scour depth maximum observed. And then the second step was more challenging. We had to find out what is the maximum flood that the bridge has seen. So to do this, we used all the USGS gauges in Texas and neighboring states. There was 930. And for each gauge, we did a flood frequency analysis to find out each year what was the maximum flood that the bridge has seen at that particular location. The problem was that many bridges don't have a gauge at the bridge. So then we had to do interpolation between location of gauges to find out exactly what happened at the bridge where we did not have a gauge. And I'll show you the interpolation. But here's a map of Texas where from 1970 to 2005, and this is the recurrence interval scale here. So red, it's like a weather map if you wish. If it's red, it's a big scale, so you're around 250, the recurrence interval, 250-year flood. The blue would be a low flood, and so on. And of course, this is from 1970 to 2005, but if you go from 1920 to 2005, now the chances are that you got much bigger floods, and so the map looks a lot more red. Then we had the recurrence interval, and we had to get to the velocity, and we went through the flow. So this is a relationship between the flow and the recurrence interval. And that's the relationship between the 5 minutes, is that it? Thank you, Paul. So here we have the relationship between the velocity and the recurrence interval. What's interesting is that, as you can see, the velocity is, there's significant nonlinearity. That's a recurrence interval to the power 0.1. So if this is 500-year flood, let's say, and the bridge has seen 80-year flood, you have 500 over 80 to the power 0.1. The actual velocity for the 500-year flood is only 10, 20% higher than the 80-year flood that you had. In order to get confidence on this interpolation technique between gauges, we played the following, we used the following process. 1, 2, 3, 4, 5 gauges. We took gauge number 5 out. We used 1, 2, 3, 4 to predict what would happen at 5, but we had the right answer because there was actually a gauge at number 5. And then we compared. Here's a frequency distribution, frequency of occurrence, a vertical axis, and the difference between predicted and measured on the horizontal axis for the velocities. You can see that on the average, we're very close, and that the standard deviation is about 0.2, so plus or minus 20%. Step 3 was so now we had the maximum observed depth, we had the maximum observed velocity, and we might be worried about the 500-year flood or the 100-year flood, so we know V future of a VMO, we know ZMO, we got to find out Z future. And to do that, we did a lot of simulations, and each blue dot here is one simulation varying a number of things, and to be conservative, we selected the top line here, relationship between the ratio of future scour depth over maximum observed scour depth as a function of V future of a VMO. All this is embedded in the software. Future scour, and then you compare the future scour depth that you've predicted to the actual value of the. We used that on 15 bridges that were selected by TxDOT. 12 were scour critical, 3 were stable. We used the OMS, 6 scour critical bridges turned out to be stable by the observation method, and the 3 stable were found stable, so there was no false negative created by the methodology. And here are some of the results. This is observation method, HEC 18. Observation method, HEC 18. Observation method, HEC 18. And sometimes it's the reverse. If you look at this case, for example, here is HEC 18 observation method. So it's not always the case that the observation method gives you less scour than HEC 18. Sometimes HEC 18 gives you the other side of the picture. Anyway, drawbacks. The method requires a good network of flow gauges. It cannot be used for new bridges because you need the observation. You have to estimate it filling. That's a limitation of the method, and in the software you have a place where you can put your estimate. And we've been doing quite a bit of studying on infilling. And then it's not yet developed for layered soil, so be very careful. If you have a very erosion-resistant layer on top of a very erodible layer, that's not a good method to use. Because if you punch through that erosion-resistant layer into the erodible layer, then you get yourself in trouble with this method. The advantages, valuable tool to prioritize bridge repair, countermeasure decision, asset management. It can serve as an input to FHW risk approach, part of the practical design. No need for erosion testing, no need for EFA. It's the actual soil, the actual flow history, the actual geometry is based on observed measurements. Again, I'll show you the difference. HEC 18 is based on flume test. There's a scale problem. It's the wrong, worse soil, fine sand. Simplified geometry, simplified single velocity. The OMS uses full scale, the right soil at the site, the exact geometry, exact velocity. This TAMU OMS, I told you it took about $1 million to develop it, and I'll be happy to send it to you for free. Unfortunately, I did a TRB webinar about a week ago, and one of the questions, did you do Hawaii? Oops, sorry, I didn't. And did you do Alaska? Oops, sorry, I didn't. And so it's the continental United States. Thank you for your attention.
Thank you, Jean-Louis. Any questions?
Very good.
this method also useful in gravel bed screens?
For
Gravel beds?
gravel bed? If it's whatever soil is at the location of the bridge, you're simply observing what has occurred in the past, and you're extrapolating on the basis of, so in the extrapolation, the one, you remember the one with all the blue dots? There are about 50 of those relationships, because each one of those relationships is for different soil categories from the chart that I showed. So the gravel is in the third category, I think. And so you have to input the diameter of the pier, you know, the general size of the pier, or abutment or contraction, whatever the case is, and then the soil type, and I forget what else, but it's a two-page, two screens software.
Thank you.
Yes.
Did you compute how the error changed when the time between the observed event and the measurements of the scour hole depth occurred?
Well, that's the problem with infilling. And so we've done a fair amount of work with infilling, but we haven't solved the problem. And that's why we leave in the software a location where you can input your best estimate of infilling. But so it's a shortcoming of this method, no doubt. But it's also a shortcoming of our practice, all of us, because we base our decisions on infilled hole measurements. If there is infilling, we go over there and we say, okay, we've got 3 feet of scour, not a big problem. We could have had 10 feet during the storm. I really believe we need to pay attention to infilling. There's a need in my mind for a project on studying infilling.
Anyone else? Very good. Help me congratulate or thank Dr. Briaud.